Hey, welcome to Napewave. I'm so happy you're here with me tonight. Find yourself a cozy spot, maybe grab a warm cup of tea, or wrap yourself in your favorite blanket, because we're about to embark on a gentle journey together. You know, there's something truly magical about taking a moment to slow down and explore the wonders that surround us every single day, yet often go unnoticed in our busy lives. Tonight, we're going to let our minds wander and our imaginations soar as we discover stories that have been unfolding for billions of years. Right above our heads, today, we are diving into the fascinating world of the story of Moonlight, Reflections. In darkness, picture this with me for a moment. You step outside on a clear evening, and there it is, hanging in the velvet sky, like a gentle beacon of hope. The moon, our closest celestial companion, bathing everything around you in its soft, silvery glow. But have you ever wondered about the incredible journey that light takes before it reaches your eyes? Tonight, we're going to uncover the secrets of moonlight, following its path from the depths of space through time itself, and into the quiet moments of our everyday lives. Let me tell you a story that began long before the first human ever looked up at the night sky in wonder. Our tale starts not with the moon itself, but with our brilliant sun, that magnificent ball of fire that sits at the center of our solar system, constantly pouring out light and energy into the vast emptiness of space. You see, what we call moonlight isn't really moonlight at all. It's sunlight that has taken a most extraordinary detour on its journey through the cosmos. Imagine, if you will, a single photon of light born in the nuclear furnace of the sun's core. This tiny particle of energy begins an incredible adventure that will take it through layers of stellar plasma, across 93 million miles of empty space, and then on a second journey of nearly 250,000 miles more. But here's where our story becomes truly enchanting. That photon doesn't travel in a straight line to reach us. Instead, it takes what we might call the scenic route, bouncing off the surface of our moon before finally arriving at Earth, to create the gentle illumination we cherish on clear nights. The process is actually quite similar to how you might use a mirror to redirect a beam of light around a corner. Except our moon is doing this on a cosmic scale every single night. When sunlight strikes the lunar surface, something beautiful happens. The moon's rocky, dust-covered terrain acts like billions of tiny mirrors, each grain of lunar soil reflecting and scattering the incoming solar radiation back out into space. Some of that reflected light happens to travel in our direction, and when it reaches Earth's atmosphere, we perceive it as that soft, ethereal glow we call moonlight. What makes this reflection so special is that the moon doesn't reflect light, like a perfect mirror would. If it did, we would only see a brilliant point of light in the sky, much too bright to look at comfortably. Instead, the moon's surface is what scientists call a diffuse reflector. This means that when sunlight hits the lunar terrain, it bounces off in many different directions rather than in a single, focused beam. The result is that gentle, even illumination that has inspired poets, lovers, and dreamers throughout human history. The lunar surface reflects only about 12% of the sunlight that reaches it, a property scientists call albedo. To put this in perspective, fresh snow reflects about 90% of sunlight, while charcoal reflects only about 4%. Our moon falls somewhere in the middle, with an albedo similar to that of charcoal or dark soil. This relatively low reflectivity is why the moon appears as a soft, gentle light rather than a blazing beacon in our night sky. But here's something truly fascinating. The quality of moonlight changes throughout the month as our perspective on the moon shifts. During a new moon, when the moon is positioned between Earth and the sun, We don't see any moonlight at all because the illuminated side of the moon faces away from us. As the moon moves in its orbit around Earth, we begin to see more and more of its sunlit surface, creating the waxing crescent, first quarter, waxing gibbous, and finally the full moon phases. During a full moon, when Earth sits between the sun and moon, we see the entire illuminated face of our celestial companion. This is when moonlight is at its brightest, casting shadows on Earth and providing enough illumination to read by if you have good eyesight. On such nights, the moon can appear up to 10 times brighter than during its crescent phases, transforming landscapes into dreamy, silver-washed scenes that seem to belong more to fairy tales than to our everyday world. The journey of moonlight doesn't end when it leaves the lunar surface. As this reflected sunlight travels through space toward Earth, it carries with it the story of its lunar encounter. The moon's composition, primarily made up of rocks rich in oxygen, silicon, magnesium, and iron, subtly influences the spectrum of light that gets reflected back to us. This is why moonlight has a slightly different color quality than direct sunlight, appearing more blue-white to our eyes than the yellowish glow of the sun during the day. When moonlight finally reaches Earth's atmosphere, it undergoes yet another transformation. Our planet's gaseous envelope acts like a vast, ever-changing lens, bending and filtering the incoming lunar illumination. Water vapor, dust particles, and other atmospheric components scatter some wavelengths of moonlight more than others, which is why the moon can appear to change color from white to yellow to orange to red, depending on atmospheric conditions and the moon's position in the sky. This atmospheric interaction is particularly dramatic when the moon is low on the horizon. Just as the sun appears red or orange when it rises or sets, the moon takes on warm, rich colors when it's positioned near the horizon line. This happens because moonlight must travel through more of Earth's atmosphere to reach us when the moon is low in the sky. And our atmosphere preferentially scatters blue and green wavelengths, while allowing red and orange wavelengths to pass through more easily. To truly understand the magic of moonlight, we need to step back in time, way back, to about 4.5 billion years ago, when our solar system was still a chaotic, violent place, filled with colliding rocks and swirling clouds of cosmic debris. The story of how our moon came to be is one of the most dramatic tales in the history of our cosmic neighborhood, and it directly impacts every gentle beam of moonlight that graces our nights today. Picture the early Earth as a hellish world, constantly bombarded by asteroids and comets, its surface a molten sea of liquid rock glowing red-hot against the black of space. This was a time called the Late Heavy Bombardment, when the gravitational dance of the giant planets was still settling into the stable orbits we know today, sending countless chunks of rock and ice careening through the inner solar system. Into this chaotic scene came a Mars-sized planetary body that scientists have named Theia, after the Greek goddess who was the mother of the moon goddess Selene. They had been forming in the same region of the solar system as Earth, gathering mass and momentum as it swept up cosmic debris in its path. But gravitational interactions with other growing planets eventually sent Theia on a collision course with our young Earth. The impact, when it came, was beyond anything we can easily imagine. They struck Earth at an angle, not head-on, but like a cosmic billiard ball hitting another at just the right trajectory to send both spinning. The collision released more energy than all the nuclear weapons ever built could produce if detonated. Simultaneously, the force was so tremendous that it literally vaporized much of both Theia and Earth's outer layers. sending countless trillions of tons of molten rock and metal spiraling out into space. This cosmic catastrophe might seem like the end of the story, but it was actually the beginning of something beautiful. The debris from the collision didn't simply drift away into space. Much of it remained trapped in Earth's gravitational field, forming a vast ring of molten rock and vaporized metal that orbited our battered planet like the rings of Saturn, but made of liquid fire instead of ice and rock. Over the course of just a few hundred years, a mere blink of an eye in cosmic terms, this ring of debris began to coalesce under its own gravity. Particles collided and stuck together, growing larger and larger until they formed a new celestial body, our moon. This process, called accretion, transformed the scattered remnants of a cosmic collision into the serene, created sphere that now lights our nights with borrowed sunlight. The newly formed moon was initially much closer to Earth than it is today, perhaps only about 15,000 miles away, compared to the current distance of about 240,000 miles. From Earth's surface, it would have appeared enormous in the sky, perhaps 20 times larger than the moon we see today. The gravitational interaction between the young Earth and this nearby moon was intense, creating massive tidal forces that may have generated tsunamis hundreds of feet high, twice daily, but over millions and millions of years. Tidal forces gradually pushed the moon away from Earth into the more distant, stable orbit we observe today. This process is actually still continuing. The moon moves away from Earth by about 1.5 inches every year, a distance so small we can only measure it using laser reflectors placed on the lunar surface by Apollo astronauts. The violent birth of our moon explains many of its unique characteristics that directly affect the moonlight we see today. Because the moon formed from the debris of a massive collision, it has a composition that's remarkably similar to Earth's outer layers, but with some key differences. The moon is depleted in volatile elements like water and has a much smaller iron core relative to its size, which affects how it reflects sunlight back to us. The moon's surface composition is dominated by a type of rock called anorthosite, which formed when the early moon was covered by a global ocean of molten rock called a magma ocean. As this ocean cooled over hundreds of millions of years, lighter minerals floated to the surface, while heavier ones sank toward the interior, creating the layered structure we see today. The light-colored highlands we observe on the moon's surface are primarily composed of these floating minerals, which give them their distinctive pale appearance that reflects sunlight so beautifully. The darker areas of the moon, which early astronomers mistakenly thought were seas, and thus named Maria, Latin for seas, are actually vast plains of solidified lava that formed when massive asteroid impacts cracked the lunar crust and allowed molten rock from the interior to flow out onto the surface. These darker regions reflect less sunlight than the brighter highlands, creating the intricate pattern of light and shadow that gives the full moon its distinctive face. The features that different cultures have interpreted as everything, from a rabbit to a man to a woman throughout human history. Understanding the moon's origin helps us appreciate just how remarkable it is that we have moonlight at all. The collision that created our moon was essentially a cosmic accident. If they had struck Earth at a slightly different angle or with different timing, we might not have a moon at all, or we might have ended up with multiple smaller moons. Or the collision might have been so devastating that it destroyed our planet entirely. Instead, we received this perfect companion, positioned at just the right distance to provide gentle illumination without overwhelming our night sky. The moon's formation also stabilized Earth's rotation and gave us our regular seasons. Without the moon's gravitational influence, Earth would wobble chaotically on its axis, creating wild climate fluctuations that might have prevented complex life from evolving. In a very real sense, we owe our existence and our ability to stand outside on a clear night and marvel at moonlight to that cosmic collision 4.5 billion years ago. As we continue our gentle exploration of moonlight's mysteries, let's turn our attention to one of the most mesmerizing aspects of our lunar companion, the way it changes its appearance in a predictable, rhythmic cycle that has served as humanity's first calendar and timekeeper. The phases of the moon create an ever-changing display of light and shadow that transforms not just the appearance of our night sky, but the very quality and intensity of the moonlight that reaches us here on Earth. Imagine you're watching a cosmic dance that takes place over the course of about 29.5 days. This dance is the orbital waltz between Earth, Moon, and Sun, and it creates one of the most reliable and beautiful patterns in nature. At any given moment, half of the moon is illuminated by sunlight, just as half of Earth is always experiencing daytime. But because the moon orbits around Earth, our perspective on that illuminated half constantly changes, creating the phases we observe from our earthbound vantage point. The cycle begins with the new moon, when our satellite is positioned between Earth and the Sun. During this phase, the illuminated side of the moon faces completely away from us, toward the Sun, leaving the side we can see in darkness. There's no moonlight during a new moon. The night sky is at its darkest, revealing countless stars that are usually outshone by lunar illumination. It's during these dark nights that astronomers prefer to make their observations, when the absence of moonlight allows them to peer deepest into the cosmos. But within just a day or two after the new moon, something magical begins to happen. As the moon continues its eastward journey around Earth, a thin sliver of its illuminated edge becomes visible from our planet. This is the waxing crescent phase, and it marks the return of moonlight to our nights. That delicate crescent, hanging like a cosmic smile in the twilight sky, provides just enough illumination to cast the faintest of shadows and give the landscape a mysterious, ethereal quality. The word waxing comes from an Old English word, meaning growing, and it perfectly describes what happens over the next week or so. Each night, the illuminated portion of the moon that we can see grows larger, creating more and more moonlight. The crescent thickens, transforming gradually into a half-moon, which astronomers call the first quarter phase because the moon has completed 1/4 of its orbit around Earth. During the first quarter phase, the moon rises around midday and sets around midnight, providing evening moonlight but leaving the pre-dawn hours dark. The quality of moonlight during this phase is particularly beautiful, bright enough to illuminate pathways and read by, but not so bright as to wash out the stars entirely. It's during first quarter that moonlight creates some of its most dramatic shadows, with the sharp contrast between the illuminated and dark portions of the lunar surface clearly visible to the naked eye. As the moon continues waxing, it enters the gibbous phase, another wonderful old word that comes from Latin and means humpbacked. The waxing gibbous moon appears more than half illuminated but not yet full, creating increasingly bright moonlight that begins to dominate the night sky. During this phase, the moon rises in the afternoon and sets in the early morning, providing moonlight for most of the night. The crescendo of this lunar light show arrives with the full moon, when Earth sits directly between the sun and moon, allowing us to see the entire illuminated face of our celestial companion. Full moonlight is truly spectacular, up to 10 times brighter than light from a crescent moon, and bright enough to trigger photosynthesis in some plants. On a clear night with a full moon, you can easily walk through a forest, read a book, or engage in detailed outdoor activities using nothing but reflected sunlight that has bounced off the lunar surface. But the full moon represents the peak of the cycle, and what follows is equally beautiful in its own way. As the moon continues its orbital journey, we begin to see less and less of its illuminated face, and the amount of moonlight gradually decreases. This is called the waning phase, from another Old English word meaning shrinking or decreasing. The waning gibbous phase follows the full moon, providing bright moonlight in the early evening but leaving the later night hours, progressively darker as the moon sets earlier each night. This phase transitions into the third quarter or last quarter, when once again half of the visible moon appears illuminated. But unlike the first quarter, the last quarter moon rises around midnight and sets around midday, providing moonlight primarily in the pre-dawn hours. The cycle concludes with the waning crescent phase, when that familiar smile-shaped sliver appears again, but this time in the early morning sky just before sunrise. The waning crescent provides the gentlest moonlight of all, just a whisper of illumination in the pre-dawn darkness before fading into the brightening sky as the sun rises. What makes this entire cycle so remarkable is its reliability and precision. Unlike the weather, which can be unpredictable, or the seasons, which change gradually over months, the lunar phases follow an exact schedule that has remained constant for billions of years. This predictability made the moon humanity's first reliable calendar, allowing ancient civilizations to track time, plan agricultural activities, and organize religious ceremonies. The changing intensity of moonlight throughout the lunar cycle has profound effects on life here on Earth. Many animals time their reproductive cycles to coincide with specific moon phases, taking advantage of either the bright illumination of the full moon or the darkness of the new moon for mating, nesting, or migration activities. Some marine creatures, particularly those living in tidal zones, synchronize their reproductive cycles not just with the moon phases but with the specific tidal patterns that the moon creates through its gravitational pull. Even plants respond to the lunar cycle. Though this is a subject of ongoing scientific research, some studies suggest that certain plants grow faster during the full moon, possibly because the additional nighttime illumination allows for extended periods of photosynthesis. Traditional farmers have long believed in planting and harvesting according to lunar phases, and while modern science is still investigating these claims, there's growing evidence that moonlight does indeed influence plant growth and development in subtle but measurable ways. The quality of moonlight also changes throughout the lunar cycle in ways that go beyond simple brightness. During crescent phases, the low angle of illumination on the lunar surface creates enhanced contrast, making crater edges and mountain ranges appear more dramatic and three-dimensional. During the full moon, when sunlight strikes the lunar surface, nearly head-on from Earth's perspective, this dramatic shadowing disappears, and the moon appears as a flat, bright disk with relatively little surface detail visible. This changing appearance throughout the month means that moonlight itself has different characteristics at different times. The sharp, contrasty illumination from a crescent moon creates dramatic shadows and highlights that can make familiar landscapes appear mysterious and otherworldly. The bright, even illumination from a full moon, on the other hand, provides the steady, reliable light that has guided nighttime travelers for millennia. As we delve deeper into the enchanting world of moonlight, let's explore one of its most subtle yet fascinating aspects, the way this reflected sunlight appears different from the direct light of our sun, and how our eyes and brains work together to perceive and interpret these gentle nighttime illuminations. This is a story that bridges astronomy and biology, revealing surprising connections between cosmic phenomena and the intricate workings of human vision. You might assume that since moonlight is simply reflected sunlight, it would have exactly the same color as the sunlight we see during the day. And in one sense, you'd be correct. The light leaving the sun and eventually reaching us after bouncing off the moon does start with the same spectrum of colors. But something fascinating happens during that cosmic journey from sun to moon to Earth, subtly transforming the quality of light in ways that create the distinctive appearance we associate with moonlight. The transformation begins at the lunar surface itself. Our moon isn't a perfect mirror. Instead, it's covered with a fine layer of dust and debris called regolith, created by billions of years of meteorite impacts. This lunar soil has some very specific optical properties that selectively affect different wavelengths of light. The moon reflects blue and violet wavelengths slightly more efficiently than red and yellow wavelengths, which means that technically, moonlight is actually slightly bluer than direct sunlight. But here's where the story becomes really interesting. Most people perceive moonlight as having a warm, yellowish or silver-white appearance, not blue. This apparent contradiction reveals something wonderful about how our visual system works and adapts to different lighting conditions. The human eye contains two main types of light-sensitive cells, rods and cones. During the day, our cone cells, which are sensitive to color and fine detail, but require relatively bright light to function, do most of the work of vision. At night, however, when light levels drop dramatically, our rod cells take over. Rod cells are incredibly sensitive to light, about 1,000 times more sensitive than cone cells, which allows us to see in conditions that would otherwise leave us completely blind. But rod cells come with a trade-off. They don't detect color at all. They only respond to the brightness or intensity of light, creating what is essentially a black and white image in our brains. This is why the world appears to lose its color in moonlight. That beautiful garden that's full of vibrant reds, yellows, and greens during the day appears as a landscape of silver, gray, and black under the moon's glow. It's not that the colors aren't there. The moonlight reflecting off those flowers and leaves contains all the same color information as sunlight. It's that our eyes have switched to a different mode of vision that prioritizes sensitivity over color discrimination. But our visual system is even more sophisticated than this simple explanation suggests. In moderate moonlight conditions, say during a bright full moon on a clear night, both our rod and cone cells are active simultaneously, creating what vision scientists call mesopic vision. This mixed mode of seeing allows us to perceive some color information while still maintaining the high sensitivity we need for nighttime vision. This is why moonlight scenes often appear to have a subtle color cast, typically described as blue, silver, or sometimes pale green. These colors aren't entirely imaginary. They represent our visual system's attempt to process the subtle color information that is present in moonlight, filtered through the complex interactions between our rod and cone cells and interpreted by our brain's sophisticated visual processing centers. The perceived color of moonlight is also strongly influenced by atmospheric conditions and the moon's position in the sky. When the moon is low on the horizon, its light must travel through more of Earth's atmosphere to reach us, just like sunlight at sunrise or sunset. This extra atmospheric journey preferentially scatters blue wavelengths while allowing red and yellow wavelengths to pass through more easily, giving the low moon a warm, golden, or orange appearance. High in the sky, when moonlight travels through less atmosphere, it retains more of its natural blue-shifted character. This is when moonlight appears most silver-white or pale blue to our eyes, creating those crisp, ethereal nighttime scenes that seem almost otherworldly in their beauty. The quality of the atmosphere, its humidity, dust, content, and temperature, all influence how moonlight appears, making each night's illumination subtly unique. Different phases of the moon also create different qualities of light that our eyes interpret in various ways. During crescent phases, when the moon appears as a thin sliver in the sky, the lighting is typically warmer in appearance because the lunar surface is illuminated at a very shallow angle, which emphasizes the light-scattering properties of the lunar soil. During the full moon, when sunlight strikes the lunar surface nearly head-on from Earth's perspective, the light appears cooler and more silver-white. The psychological and emotional impact of moonlight's apparent color is profound and has influenced human culture for thousands of years. The cool, blue-silver quality of bright moonlight has become associated with mystery, romance, and magic in countless stories, poems, and songs. There's something about this ethereal illumination that seems to transform ordinary landscapes into scenes from fairy tales, making familiar places appear strange and wonderful. Photography reveals another interesting aspect of moonlight's color. When photographers take long exposure images by moonlight, the resulting pictures often show landscapes that appear to have been taken during the day, complete with blue skies and natural-looking colors. This happens because camera sensors, unlike human eyes, don't switch between different types of light-sensitive elements based on brightness levels. The camera simply collects all the available light over an extended period, revealing the full spectrum of colors that are present in moonlight, but invisible to our night-adapted eyes. These photographic revelations help us understand that moonlight truly does contain all the colors of sunlight. They're just too dim for our color-sensitive cone cells to detect under normal viewing conditions. It's a beautiful reminder that there's always more to any natural phenomenon than meets the eye, and that the tools of science can reveal hidden aspects of familiar experiences. The study of moonlight's colors has practical applications as well. Understanding how human vision works in low-light conditions is crucial for designing everything from automobile headlights to street lighting to military equipment. The knowledge gained from studying how we perceive moonlight has contributed to improvements in night vision technology, aviation safety systems, and even the design of computer and smartphone screens that are easier on our eyes during nighttime. Recent research has also revealed that exposure to natural light cycles, including the subtle illumination provided by moonlight, plays an important role in regulating our circadian rhythms, the internal biological clocks that govern our sleep-wake cycles and many other physiological processes. The gentle, blue-shifted light of the moon may actually help maintain healthy sleep patterns in ways that artificial lighting cannot fully replicate. One of the most profound and visible demonstrations of the moon's influence on our planet comes not from moonlight itself, but from the gravitational force that our lunar companion exerts on Earth. This same celestial body that provides us with gentle, nighttime illumination is also responsible for one of the most fundamental rhythms of our planet, the rise and fall of ocean tides that have shaped coastlines, influenced marine ecosystems, and guided human activities for millions of years. To understand this connection, We need to think about gravity not as a simple downward force, but as an invisible thread that connects every object in the universe to every other object. The Moon, despite being much smaller than Earth, exerts a gravitational pull on our planet that is strong enough to literally lift the oceans. But this lifting isn't uniform across Earth's surface. It's strongest on the side of Earth, facing the Moon, and weakest on the side facing away from the Moon. Picture Earth as if it were covered entirely by a global ocean. The water on the side facing the Moon feels the Moon's gravitational pull most strongly, causing it to bulge outward toward our lunar companion. At the same time, the water on the opposite side of Earth, the side facing away from the Moon, also bulges outward, but for a different reason. This happens because Earth itself is being pulled toward the Moon more strongly than the water on the far side, effectively leaving that distant water behind in space. The result is that Earth's oceans form to bulges, one facing the Moon and one facing away from it. As our planet rotates once every 24 hours, different parts of Earth's surface pass through these bulges, creating the regular pattern of high and low tides that we observe at coastlines around the world. In most places, this creates 2 high tides and 2 low tides each day, separated by about 6 hours and 12 minutes. But here's where the story becomes even more interesting. The Sun also exerts a gravitational influence on Earth's oceans, though it's about half as strong as the Moon's influence, despite the Sun's vastly greater mass. This is because gravitational force depends not just on mass but also on distance, and the Sun is so much farther away that its tidal influence is significantly reduced. However, when the Sun, Moon, and Earth align, which happens during new Moon and full Moon phases, their gravitational effects combine to create especially high spring tides and especially low tides. Conversely, when the Sun and Moon are at right angles to each other relative to Earth during first and third quarter Moon phases, their gravitational effects partially cancel each other out, creating more moderate neap tides with smaller differences between high and low water levels. This means that the brightness of moonlight and the strength of tides are intimately connected, both following the same lunar cycle that has regulated life on Earth for billions of years. The connection between moonlight and tides extends far beyond simple gravitational mechanics. Many marine organisms have evolved to time their reproductive cycles to coincide with specific combinations of lunar phase and tidal conditions. Grunion, small fish that live along the California coast, time their spawning to coincide with the highest spring tides, which occur during full and new moon phases. The fish ride the waves onto beaches during these extreme high tides, lay their eggs in the sand, and return to the sea, trusting that the eggs will remain safely buried until the next series of spring tides arrives to carry the newly hatched fish back to the ocean. Coral reefs throughout the world also synchronize their reproductive activities with lunar cycles. Many coral species release their eggs and sperm into the water simultaneously during specific moon phases, creating underwater blizzards of genetic material that increase the chances of successful fertilization. These mass spawning events often occur during full moon phases, when the combination of bright moonlight and strong tides creates optimal conditions for reproduction. The relationship between moonlight and tides also influences the behavior of countless other marine creatures. Many species of sea turtles prefer to nest during dark moon phases, when the absence of moonlight makes it easier for them to approach beaches undetected by predators. However, the timing of their nesting is also influenced by tidal cycles, as they need high tides to help them navigate through coastal waters and reach suitable nesting sites. For centuries, humans have also recognized and utilized the connection between lunar phases, tides, and marine life. Fishermen around the world have traditionally planned their activities around moon phases, knowing that fish behavior changes in response to tidal patterns and lunar illumination. Some species are more active during bright moonlit nights, while others prefer the darkness of new moon phases. Shellfish harvesting, seaweed collection, and many other marine activities have been timed to lunar cycles for thousands of years. The influence of lunar tides extends inland as well, though in ways that are often less obvious than ocean tides. Large lakes can experience small tidal variations, and the solid earth itself actually rises and falls by several inches, twice daily in response to the moon's gravitational pull. These earth tides are too small for us to feel directly, but they can be measured with sensitive instruments and actually affect the operation of some scientific equipment. Even the atmosphere experiences tidal effects from the moon's gravitational influence. Atmospheric tides create subtle variations in air pressure that follow lunar cycles, though these effects are generally much smaller than the pressure changes caused by weather systems. However, some researchers have suggested that atmospheric tides might influence weather patterns in ways that we're only beginning to understand. The study of tidal forces has practical applications that extend far beyond marine biology and navigation. Understanding how the moon's gravity affects Earth is crucial for precisely tracking satellite orbits, planning space missions, and operating sensitive scientific instruments. The Global Positioning System, GPS, that many of us use daily must account for both Earth tides and atmospheric tides to maintain its accuracy. Looking toward the future, the relationship between moonlight and tides may become even more important. As humans develop new technologies for harvesting tidal energy, tidal power plants, which generate electricity from the predictable rise and fall of ocean tides, rely on the same lunar cycles that create moonlight. These facilities represent a form of renewable energy that is ultimately powered by the gravitational dance between Earth and Moon, the same cosmic choreography that brings us gentle illumination on clear nights. Climate change and rising sea levels are also making tidal predictions more important than ever for coastal communities around the world. Understanding how lunar cycles interact with changing ocean conditions will be crucial for protecting coastal infrastructure and natural habitats from the increasing frequency of extreme tidal events. Perhaps most remarkably, recent research suggests that the moon's influence on tides may have been crucial for the evolution of life on Earth. The regular rise and fall of tides in ancient seas created constantly changing environments at the boundary between land and water, precisely the conditions that may have encouraged the first aquatic life forms to develop adaptations for surviving on land. In this sense, we may owe our very existence to the same lunar companion that continues to light our nights with reflected sunlight. As darkness falls and moonlight begins to bathe the landscape in its silver glow, an entirely different world awakens around us. While we humans typically retreat indoors when the sun sets, countless other creatures are just beginning their day, emerging from hidden shelters to hunt, forage, communicate, and reproduce under the gentle illumination of our lunar companion. The story of how moonlight influences nocturnal life reveals a complex web of adaptations, behaviors, and evolutionary strategies that have developed over millions of years. Let's begin with one of the most obvious examples of nocturnal activity: the haunting calls of owls echoing through moonlit forests. These magnificent birds of prey have evolved extraordinary adaptations for hunting in low-light conditions, and moonlight plays a crucial role in their success. An owl's eyes are proportionally much larger than those of diurnal birds, gathering every available photon of moonlight to create detailed images of their prey moving through the darkness below. But owls don't rely on vision alone. Their asymmetrically positioned ears allow them to pinpoint the exact location of a mouse rustling through leaves by sound alone, while their specially adapted feathers enable silent flight that prevents prey from hearing their approach. During bright moonlit nights, owls can combine these acoustic hunting skills with enhanced visual information, making them incredibly effective predators. The interplay between moonlight intensity and owl hunting success demonstrates how lunar cycles can influence entire food webs. Many nocturnal mammals have evolved similar adaptations for making the most of available moonlight. The large forward-facing eyes of nocturnal primates, like bush babies and tarsiers, gather moonlight efficiently, while their enhanced light-sensitive cells allow them to navigate through forest canopies with remarkable agility. These adaptations are so effective that these animals can leap confidently from branch to branch in light conditions that would leave humans functionally blind. But moonlight creates both opportunities and challenges for nocturnal animals. While predators benefit from the enhanced visibility that moonlight provides, prey animals face increased danger during bright lunar phases. Many small mammals, such as mice and voles, actually reduce their activity during full moon nights, remaining hidden in burrows and dense vegetation to avoid detection by owls, foxes, and other predators that hunt more effectively in moonlight. This creates what ecologists call landscape of fear, a constantly shifting pattern of safe and dangerous areas that changes with lunar phase, weather conditions, and seasonal variations in vegetation cover. During new moon phases, when darkness provides better cover, small mammals become more active, venturing farther from shelter to forage and explore. This lunar rhythm of predator and prey activity cascades through entire ecosystems, influencing everything from seed dispersal patterns to plant growth rates. The insect world reveals some of the most fascinating adaptations to moonlight. Many moths use the moon as a navigation aid, maintaining a constant angle to the lunar disk to fly in straight lines across the landscape. This behavior, called transverse orientation, works perfectly when the moon is the only bright light source in the sky. However, artificial lights can disrupt this navigation system, causing moths to spiral helplessly around street lamps and porch lights in a phenomenon that demonstrates how evolution hasn't yet adapted to human modifications of the nighttime environment. Fireflies present another captivating example of how insects interact with moonlight. These beetles produce their own bioluminescent signals for communication, but the effectiveness of their light displays varies dramatically with lunar phase. During dark new moon nights, firefly flashes are highly visible and effective for attracting mates. However, during bright full moon nights, their bioluminescent signals become much less conspicuous, and many firefly species actually reduce their signaling activity or change their flashing patterns to compensate for the competing illumination. From moonlight, marine environments reveal equally remarkable adaptations to lunar illumination. Many coral reef fish that are active during the day retreat to hiding places as evening approaches, but a completely different community of nocturnal fish emerges to take advantage of the nighttime environment. Flashlight fish, equipped with bacterial light organs under their eyes, use their own bioluminescence to hunt for small prey in the darkness, while parrotfish wrap themselves in mucus cocoons that may help mask their scent from nocturnal predators. The vertical migration of marine plankton represents one of the largest daily movements of biomass on Earth, and this migration is strongly influenced by moonlight intensity. During dark nights, zooplankton rise toward the ocean surface to feed on microscopic plants and other organic matter. However, during bright moonlit nights, many of these tiny creatures remain in deeper, darker waters to avoid visual predators, like small fish and jellyfish that hunt more effectively in the enhanced illumination. This daily vertical migration creates a moving feast that supports countless marine food chains. Fish, squid, marine mammals, and seabirds all time their feeding activities to take advantage of these predictable movements of prey. The relationship between moonlight intensity and plankton behavior thus influences the feeding success of animals, ranging from tiny fish larvae to massive blue whales. Plant life also responds to moonlight in ways that scientists are still discovering. While moonlight is far too dim to drive significant photosynthesis, some plants do exhibit subtle responses to lunar illumination. Certain flowers open specifically during nighttime hours to attract nocturnal pollinators like moths and bats, and the timing of this opening may be influenced by moonlight intensity. Evening primroses, 4 o'clocks, and night-blooming cereus are just a few examples of plants that have evolved to make the most of nocturnal polygars. The seeds of some plants are also dispersed primarily by nocturnal animals, creating another link between lunar cycles and plant reproduction. When small mammals change their foraging patterns in response to moonlight, they inadvertently alter seed dispersal patterns as well. Seeds that travel in the fur or digestive systems of these animals end up being distributed differently across the landscape depending on lunar phase, potentially influencing the genetic structure of plant populations over time. Recent research has begun to reveal how artificial lighting is disrupting these ancient lunar rhythms. Light pollution from cities and towns creates a constant glow that can interfere with the natural darkness that many nocturnal species require for optimal survival and reproduction. Migrating birds become disoriented by city lights, while sea turtle hatchlings, which naturally orient toward the brightest horizon, historically the moonlit ocean, may instead head toward artificial lights on shore, leading them away from the safety of the water. The disruption of natural light cycles also affects the timing of seasonal behaviors in many species. Plants may bloom at incorrect times. Insects may emerge when their food sources aren't available, and the complex synchronizations between predators and prey that have evolved over millions of years can become misaligned. Understanding these disruptions has become increasingly important as urban areas continue to expand and artificial lighting becomes more pervasive. Conservation efforts now recognize the importance of preserving natural darkness for nocturnal wildlife. Dark sky preserves areas specifically protected from light pollution, provide refuges where natural lunar rhythms can continue undisturbed. These protected areas not only preserve habitat for nocturnal species, but also allow humans to experience the natural nighttime environment that our ancestors knew, landscapes illuminated only by moonlight, starlight, and the occasional flash of bioluminescence throughout human history. No celestial object has captured our imagination quite like the moon. From the earliest cave paintings to modern poetry, from ancient religious ceremonies to contemporary scientific research, moonlight has woven itself into the very fabric of human culture, inspiring countless stories, beliefs, and traditions that span every continent and civilization. The gentle illumination that streams down from our lunar companion has served not just as a source of light, but as a muse, a timekeeper, a deity, and a symbol of countless human hopes and dreams. Long before the invention of artificial lighting, moonlight was humanity's primary source of illumination after sunset. Our ancestors planned their activities around lunar cycles with the same precision that we modern humans plan around work schedules and calendar appointments. Full moon nights were times for travel, storytelling, and community gatherings, when the bright lunar illumination made it possible to continue important activities well into the night hours. The reliability of lunar phases made the moon humanity's first universal calendar. Ancient civilizations from Mesopotamia to China, from Egypt to the Americas, developed sophisticated lunar calendars that governed everything from agricultural activities to religious festivals. The word month itself derives from moon, reflecting the fundamental role that lunar cycles played in organizing human timekeeping systems. Even today, many religious and cultural celebrations, including Easter, Ramadan, and the Chinese New Year, are still timed according to lunar phases rather than the solar calendar. In ancient Greece and Rome, the moon was personified as powerful goddesses, Selene, Artemis, and Diana, who were associated with hunting, childbirth, and feminine power. These lunar deities were often depicted as beautiful women surrounded by silver light, emphasizing the ethereal, otherworldly quality of moonlight that seemed to transform ordinary landscapes into mystical realms. Temples dedicated to moon goddesses were often designed to capture and focus moonlight during specific phases, creating dramatic architectural displays that reinforced the connection between lunar illumination and divine presence. The association between moonlight and femininity appears in cultures worldwide, often connected to the observation that lunar cycles roughly correspond to human menstrual cycles. Many ancient societies believed that women were particularly influenced by moonlight, and rituals surrounding childbirth, coming of age, and other feminine life transitions were often timed to coincide with specific moon phases. These beliefs have persisted in various forms through modern times, influencing everything from folk medicine practices to contemporary spiritual movements. In Islamic culture, the crescent moon became a powerful symbol that adorns flags, architecture, and religious art throughout the Muslim world. The lunar calendar governs important Islamic observances, and the sighting of the new crescent moon marks the beginning of months, including the holy month of Ramadan. The tradition of looking for the new moon's first appearance connects modern Muslims with centuries of their ancestors who relied on careful observation of lunar phases for religious and practical purposes. Native American cultures developed rich traditions surrounding moonlight and lunar cycles, with different tribes recognizing various moons throughout the year based on seasonal activities and natural phenomena. The harvest moon, snow moon, wolf moon, and many others reflected the deep connection between lunar cycles and the rhythms of life on the land. These naming traditions recognized that moonlight's significance changed throughout the year. A bright autumn moon provided extra illumination for harvesting crops, while winter moonlight revealed animal tracks in snow and helped hunters provide for their communities. During harsh months, Chinese culture has long celebrated the Moon Festival, also known as the Moon Festival, which occurs during the full moon closest to the autumn equinox. This celebration emphasizes family reunification and features the sharing of mooncakes, round pastries that symbolize the full moon and family unity. The festival reflects the Chinese philosophical concept that the full moon represents completeness and harmony, ideals that extend from family relationships to broader social and cosmic order. The influence of Moonlight on literature and poetry cannot be overstated. From ancient Sanskrit texts to contemporary novels, writers have used lunar imagery to evoke romance, mystery, melancholy, and transformation. Shakespeare's plays are filled with moonlit scenes, from the magical forest of A Midsummer Night's Dream to the tragic balcony scene in Romeo and Juliet, that use the unique quality of moonlight to create emotional atmospheres that would be impossible to achieve with daylight settings. Romantic poets of the 18th and 19th centuries were particularly drawn to moonlight as a subject and inspiration. Lord Byron, Percy Shelley, John Keats, and many others wrote extensively about lunar illumination, using it as a metaphor for unattainable beauty, spiritual longing, and the mysterious aspects of human experience. The phrase "Moonlight Serenade" entered popular culture during this period, reflecting the association between lunar illumination and romantic expression that continues to influence music, literature, and popular culture today. Visual artists have similarly been captivated by the challenge and beauty of depicting moonlight. The Dutch Golden Age painters developed sophisticated techniques for representing nocturnal scenes illuminated by lunar light, while romantic landscape painters like Caspar David Friedrich created haunting images of moonlit forests, mountains, and seascapes that emphasized the sublime and mysterious aspects of nature. The Impressionist movement brought new approaches to capturing the subtle color variations and atmospheric effects of moonlight, with artists like Claude Monet creating series of paintings exploring how lunar illumination changed the appearance of haystacks, cathedrals, and water lily ponds. The invention of photography in the 19th century opened new possibilities for documenting and artistic interpretation of moonlight. Early photographers struggled with the technical challenges of capturing nighttime scenes, but their efforts produced some of the most evocative images in the medium's history. Long exposure photographs revealed aspects of moonlit landscapes that were invisible to the naked eye, showing familiar places transformed by the unique quality of reflected lunar illumination. Folk traditions and superstitions surrounding moonlight vary widely across cultures, but share common themes of transformation, magic, and hidden knowledge. Many cultures believe that certain activities, from gardening to healing to divination, are more effective when performed during specific moon phases. While modern science has debunked many of these beliefs, research continues to reveal subtle ways that lunar cycles do influence biological and physical processes, suggesting that some traditional knowledge may have basis in observable, natural phenomena. The association between moonlight and madness, reflected in words like lunatic and moonstruck, appears in cultures worldwide. Though scientific research has found no reliable correlation between lunar phases and human behavior or mental health, however, the persistence of these beliefs across different societies suggests something fundamental about how humans respond psychologically to the changing quality and intensity of nighttime illumination. Modern urban life has dramatically changed humanity's relationship with moonlight. Light pollution from cities and towns creates a constant artificial glow that obscures both moonlight and starlight for billions of people. Many urban dwellers have never experienced true moonlit darkness, missing out on the subtle beauty and psychological impact of natural nighttime illumination that shaped human culture for thousands of years. This disconnection from natural light cycles has prompted growing interest in dark sky movements and astronomical tourism, where people travel to remote locations specifically to experience natural nighttime conditions. These efforts recognize that access to genuine moonlight and starlight is not just an aesthetic luxury, but an important connection to the natural world and to the cultural heritage that shaped human civilization. Contemporary art and literature continue to draw inspiration from moonlight, though often with awareness of how urbanization and technology have changed our relationship with lunar illumination. Science fiction writers explore how humans might experience moonlight on other worlds, while environmental artists create installations that highlight the contrast between natural and artificial illumination. These modern works often carry themes of loss and recovery, reflecting concerns about humanity's increasing separation from natural rhythms and cycles. As we venture deeper into our exploration of moonlight, let's turn our attention to the fascinating scientific discoveries that have emerged from centuries of careful observation and study of our lunar companion. Modern astronomy, physics, and planetary science have revealed remarkable details about how moonlight is created, transmitted, and perceived, details that would have seemed like magic to our ancestors, but now provide us with a profound understanding of the complex processes that bring us this gentle nighttime illumination. The journey of understanding moonlight scientifically began with ancient Greek philosophers who first proposed that the moon shines with reflected sunlight rather than generating its own luminescence. This was a revolutionary insight for its time, requiring observers to think beyond the obvious appearance of the moon as a glowing orb and instead understand it as a rocky world that receives and redirects solar radiation. The confirmation of this theory through careful observation and mathematical analysis represented one of humanity's first major steps toward understanding our place in the cosmic system. Modern measurements have revealed precise details about the moon's reflective properties that earlier astronomers could only speculate about. The lunar surface reflects approximately 12% of the sunlight that strikes it, a property called albedo, named after the Latin word for whiteness. This relatively low reflectivity means that the moon is actually quite dark, comparable to charcoal or worn asphalt in terms of how much light it reflects. The fact that the moon appears bright to us is simply a result of the contrast between its illuminated surface and the dark background of space. The moon's albedo varies significantly across its surface, creating the patterns of light and dark that we observe with the naked eye. The bright lunar highlands, composed primarily of anorthosite rock rich in the mineral feldspar, reflect about 18% of incident sunlight. The darker lunar maria, filled with basaltic lava flows that contain iron-rich minerals, reflect only about 7% of sunlight. This variation in surface composition and reflectivity creates the intricate patterns that different cultures have interpreted as faces, animals, or mythological figures. The spectrum of reflected moonlight provides a wealth of information about lunar surface composition. Spectroscopic analysis, the study of how different materials absorb and reflect specific wavelengths of light, has allowed scientists to map the distribution of minerals across the lunar surface without ever bringing samples back to Earth. Iron-rich areas absorb more red wavelengths, appearing darker and slightly bluer in reflected light, while areas rich in titanium-bearing minerals show distinctive spectral signatures that can be detected from Earth-based telescopes. One of the most significant discoveries about moonlight came from understanding how the lunar surface scatters light. Unlike a mirror, which reflects light in a single direction, The Moon's surface exhibits what scientists call Lambertian reflection. It scatters incoming sunlight relatively evenly in all directions. This diffuse reflection is what allows us to see the Moon from any angle and creates the gentle, even illumination that characterizes moonlight rather than the harsh, focused beams that would result from specular reflection. The texture of the lunar surface plays a crucial role in creating the quality of moonlight we observe. Billions of years of meteorite impacts have pulverized the lunar surface into a fine powder called regolith, with particles ranging from microscopic dust to boulder-sized chunks. This rough, irregular surface creates complex patterns of shadowing and reflection that give moonlight its distinctive character. The same surface that appears smooth and uniform to the naked eye actually contains millions of tiny shadows and highlights that collectively produce the diffuse illumination we perceive as moonlight. Recent research has revealed that the lunar surface exhibits a phenomenon called opposition surge. It actually appears brightest when viewed from directly opposite the Sun, which corresponds to full moon phase as seen from Earth. This brightening effect occurs because, at opposition, shadows cast by surface irregularities are hidden behind the objects that create them, allowing us to see maximum reflected sunlight. This explains why the full moon appears disproportionately bright compared to other lunar phases. Not just because more of the illuminated surface is visible, but because the illumination itself is enhanced by this geometric effect. The study of how moonlight travels through space has contributed to our understanding of electromagnetic radiation and the physics of light itself. Moonlight, like all electromagnetic radiation, travels at the speed of light, approximately 186,000 miles per second. The journey from Sun to Moon takes about 8 minutes and 20 seconds, and the additional journey from Moon to Earth takes another 1.3 seconds on average. This means that the moonlight reaching us tonight actually left the Sun nearly 8.5 minutes ago, carrying information about solar conditions from that earlier time. The polarization of moonlight has revealed additional details about lunar surface properties. When sunlight reflects off the Moon, it becomes partially polarized, meaning that the light waves oscillate preferentially in certain directions, rather than randomly in all directions. The degree and angle of this polarization varies depending on the lunar phase and the composition of the reflecting surface. Scientists have used polarization measurements to study the size and shape of lunar soil particles and to better understand the physical processes that have shaped the lunar surface over billions of years. Advances in detector technology have allowed scientists to study moonlight across the entire electromagnetic spectrum, not just the visible wavelengths that our eyes can perceive. Infrared observations of moonlight revealed temperature variations across the lunar surface, showing how different materials heat up and cool down as they rotate in and out of sunlight. Ultraviolet observations can detect the presence of certain minerals and provide information about space weathering processes that gradually alter the lunar surface over geological time. The study of lunar laser ranging represents one of the most precise measurements in all of science. Since the Apollo missions placed retroreflectors on the lunar surface, scientists have been able to measure the distance between Earth and Moon with incredible accuracy by timing how long it takes laser pulses to travel to the Moon and back. These measurements have revealed that the Moon is gradually moving away from Earth at a rate of about 1.5 inches per year, confirming theoretical predictions about tidal evolution and providing precise tests of Einstein's theory of general relativity. Computer modeling has allowed scientists to predict and understand how moonlight varies over long time periods. Models can calculate the exact phase, brightness, and appearance of the moon for any date in the past or future, taking into account the complex gravitational interactions between Earth, Moon, and Sun that cause subtle variations in lunar orbit and phase timing. These models are essential for planning space missions, predicting eclipses, and understanding how lunar illumination has changed over geological time. The study of lunar samples returned by Apollo missions has provided direct information about the materials responsible for reflecting moonlight back to Earth. Chemical and mineralogical analysis of these samples has confirmed spectroscopic observations made from Earth and revealed details about lunar formation and evolution that could only be determined through direct laboratory study. The discovery that lunar rocks contain virtually no water or organic compounds helps explain the moon's distinctive reflective properties and confirms theories about its formation from high-temperature processes. Modern understanding of moonlight has practical applications that extend far beyond pure scientific curiosity. Accurate models of lunar illumination are essential for planning astronomical observations, as moonlight can interfere with the detection of faint stars and galaxies. Military and civilian navigation systems must account for lunar illumination when designing night vision equipment and satellite reconnaissance systems. Even digital photography and video production now use scientific understanding of moonlight characteristics to create more realistic artificial lighting for nighttime scenes. The study of how Earth's atmosphere affects moonlight has contributed to broader understanding of atmospheric physics and climate science. The way moonlight is scattered, absorbed, and refracted by atmospheric gases and particles provides information about atmospheric composition and structure. Changes in how moonlight appears can indicate variations in atmospheric dust, humidity, and temperature that are relevant to weather forecasting and climate. Monitoring future missions to the moon will undoubtedly reveal new details about the processes that create moonlight. Advanced spectrometers, high-resolution cameras, and in-situ analysis equipment will provide unprecedented detail about lunar surface composition and structure. As humans return to the lunar surface and potentially establish permanent bases there, our understanding of moonlight will continue to evolve, revealing new aspects of this familiar yet still mysterious phenomenon that has guided and inspired humanity throughout our history. As we continue our gentle journey through the mysteries of moonlight, we arrive at one of the most intriguing and actively researched areas of lunar influence: the potential connections between lunar cycles and human biology, behavior, and well-being. While popular culture is filled with claims about how the moon affects human behavior, the scientific reality is both more subtle and more fascinating than many of the myths and legends that have grown up around our relationship with lunar illumination. The human body operates according to complex biological rhythms that govern everything from our sleep-wake cycles to hormone production, body temperature fluctuations, and cellular repair processes. These circadian rhythms, from the Latin words meaning about a day, are primarily synchronized to the 24-hour cycle of sunlight and darkness. However, researchers have increasingly discovered that longer rhythms, including some that may be influenced by lunar cycles, also play important roles in human physiology. The most well-established connection between lunar cycles and human biology involves the relationship between moonlight and sleep patterns. While artificial lighting has largely disconnected modern humans from natural light cycles, studies of people living in environments with minimal artificial illumination have revealed subtle but measurable changes in sleep timing and duration that correlate with lunar phases. During full moon periods, when natural nighttime illumination is brightest, people tend to go to sleep slightly later and sleep somewhat less deeply than during new moon periods. These sleep changes appear to be ancient adaptations that persist, even when people are not consciously aware of lunar phase. Research conducted in sleep laboratories, where participants are isolated from external light cues, has still detected small but consistent variations in sleep patterns that follow lunar cycles. This suggests that humans may possess internal biological clocks that are sensitive to lunar periodicity, possibly as an evolutionary remnant from our ancestors, who lived more closely aligned with natural light cycles. The mechanism behind these lunar sleep effects is thought to involve the same biological systems that regulate circadian rhythms. The human brain contains a structure called the suprachiasmatic nucleus, which acts as a master biological clock by responding to light information received through the eyes. While this system is primarily tuned to the daily cycle of sunlight and darkness, it may also retain some sensitivity to the longer-term changes in nighttime illumination that accompany lunar phases. Recent research has revealed that exposure to different intensities and colors of light can significantly influence human physiology and psychology. The blue-white light characteristic of moonlight appears to have different effects on human biology than the warmer, redder light of sunset or artificial incandescent bulbs. Moonlight's spectral characteristics may influence the production of melatonin, a hormone that regulates sleep cycles, in ways that create subtle monthly rhythms in sleep quality and timing. Historical evidence suggests that before the advent of artificial lighting, humans may have lived more synchronized lives that took advantage of lunar illumination patterns. Traditional societies around the world developed cultural practices that aligned activities with lunar phases, scheduling community gatherings, celebrations, and important ceremonies to coincide with bright moonlit nights when extended activities were possible without artificial lighting. Some researchers have investigated whether human reproductive cycles show any relationship to lunar periodicity. While the average human menstrual cycle of approximately 28 days is intriguingly close to the 29.5-day lunar month, modern scientific studies have found no reliable correlation between individual menstrual cycles and lunar phases. However, some research suggests that in environments with natural lighting conditions, women's cycles may show slightly more synchronization with lunar phases than they do under artificial lighting conditions. The psychological effects of moonlight have been a subject of human fascination for thousands of years, giving rise to words like lunatic and beliefs about increased emotional volatility during full moon periods. However, extensive scientific research has failed to find reliable correlations between lunar phases and measures of human behavior such as crime rates, hospital admissions, or psychiatric episodes. The persistence of these beliefs may reflect the powerful psychological impact that bright moonlight has on human perception and mood, even if it doesn't directly influence behavior in measurable ways. What is clear is that exposure to natural light cycles, including the subtle variations in nighttime illumination provided by moonlight, can have positive effects on human health and well-being. People who spend time outdoors during different lunar phases often report subjective improvements in mood and sleep quality compared to those who experience only artificial lighting environments. This suggests that maintaining some connection to natural light cycles, including lunar cycles, may be beneficial for human health. The The rapid increase in artificial lighting over the past century has created unprecedented disruption of natural light cycles for human populations. Light pollution not only obscures our view of moonlight and stars, but also creates constant artificial illumination that can interfere with natural biological rhythms. Research in the emerging field of chronobiology, the study of biological rhythms, has revealed that exposure to artificial light at night can disrupt sleep patterns, hormone production, and other biological processes in ways that may contribute to various health problems. Some researchers have begun investigating whether periodic exposure to natural moonlight conditions might help restore healthy biological rhythms in people whose sleep cycles have been disrupted by artificial lighting. Camping trips, outdoor activities during different lunar phases, and even architectural designs that allow natural moonlight to enter sleeping areas are being studied as potential therapeutic interventions for sleep disorders and other rhythm-related health problems. The field of light therapy has developed sophisticated understanding of how different types of light exposure can be used to treat seasonal affective disorder, jet lag, and other conditions related to disrupted biological rhythms. While most light therapy focuses on bright light exposure during daytime hours, some researchers are exploring whether controlled exposure to dimmer, moonlight-like illumination during nighttime hours might also have therapeutic benefits. Cultural practices surrounding moonlight exposure may have inadvertently preserved beneficial aspects of natural light cycle exposure that modern life has eliminated. Traditional practices such as evening walks during full moon periods, outdoor meditation during different lunar phases, and agricultural activities timed to lunar cycles may all provide forms of light exposure that support healthy biological rhythms. Individual sensitivity to lunar cycles appears to vary considerably among people, with some individuals reporting strong subjective responses to lunar phases, while others notice no effects at all. This variation may reflect differences in genetic factors that influence biological rhythm regulation, lifestyle factors that affect light exposure, or psychological factors that influence awareness of and response to environmental cycles. Future research in this area will likely benefit from advances in wearable technology that can continuously monitor biological markers such as heart rate, body temperature, and activity levels over extended periods. These devices may allow researchers to detect subtle lunar cycle influences that are too small to measure with traditional research methods, but may still have meaningful effects on human health and behavior. The growing understanding of light's effects on human biology has practical implications for architecture, urban planning, and personal health practices. Designing homes and workplaces that allow appropriate exposure to natural light cycles, including gentle moonlight, may become increasingly important for maintaining human health in an urbanized world. Simple practices such as spending time outdoors during different lunar phases, reducing artificial lighting during evening hours, and choosing window treatments that allow natural moonlight to enter sleeping areas may all contribute to better alignment with natural biological rhythms throughout human history. Artists, scientists, and curious observers have been drawn to capture and preserve the ethereal beauty of moonlight, whether through paintings, photographs, or detailed written descriptions. The challenge of representing moonlight has pushed the boundaries of artistic technique and technological innovation, leading to some of the most evocative and technically sophisticated images in the history of visual art and scientific documentation. The unique visual qualities of moonlight present special challenges for anyone attempting to reproduce or record its appearance. Unlike the bright, consistent illumination of sunlight, Moonlight is subtle, constantly changing, and creates effects that are often at the very limits of human visual perception. Early artists who wanted to depict nocturnal scenes had to develop entirely new techniques and approaches, as the methods used for daylight scenes simply couldn't capture the delicate interplay of light and shadow that characterizes moonlit landscapes. Golden Age painters of the 17th century were among the first to master the art of depicting moonlight convincingly. Artists like Art van der Neer developed sophisticated understanding of how moonlight affects color perception, contrast, and atmospheric perspective. They discovered that moonlit scenes required completely different color palettes than daylight. Scenes with subtle variations of blue, silver, and gray replacing the warm colors associated with sunlight. These artists also learned to use dramatic contrasts between illuminated and shadowed areas to create the sense of mystery and drama that moonlight naturally provides. The Romantic movement of the late 18th and early 19th centuries elevated moonlit scenes to new levels of artistic importance. Painters like Caspar David Friedrich created haunting landscapes where moonlight served not just as illumination but as a symbol of the sublime, the spiritual, and the mysterious aspects of nature. These artists understood that moonlight could transform familiar landscapes into otherworldly scenes that evoked powerful emotional responses from viewers. The invention of photography in the 19th century opened entirely new possibilities for documenting moonlight, but it also presented unprecedented technical challenges. Early photographic materials were extremely insensitive to light, requiring exposure times of many minutes or even hours to capture enough light to create an image. Moonlight photography pushed these limitations to their absolute limits, often requiring exposures so long that the moon's movement across the sky would blur into streaks of light rather than sharp circular discs. Pioneer photographers like Ensa Adams developed innovative techniques for capturing moonlit landscapes that revealed aspects of nocturnal scenes invisible to the naked eye. Long exposure times allowed cameras to accumulate light over extended periods, creating images that showed far more detail in shadowed areas than human eyes could perceive in real time. These photographs revealed that moonlit landscapes contained rich textures, subtle color variations, and complex patterns of illumination that were largely hidden from direct visual observation. The development of more sensitive photographic materials and techniques gradually made moonlight photography more accessible, but it remained a challenging and specialized pursuit. Photographers had to master complex calculations involving exposure times, film sensitivity, and the brightness variations that occur during different lunar phases. They also had to understand how different atmospheric conditions, humidity, dust, and temperature variations affected both the appearance of moonlight and the photographic process itself. Color photography presented additional challenges for documenting moonlight accurately. While moonlight appears silver or blue-white to the human eye, photographic films often recorded it with different color casts, depending on their spectral sensitivity and the processing techniques used. Learning to represent the subtle colors of moonlit scenes required photographers to develop new understanding of how photographic materials responded to different wavelengths of light and how processing techniques could be adjusted to achieve more natural-looking results. Digital photography has revolutionized moonlight capture, making it possible for amateur photographers to achieve results that would have required expert skill and specialized equipment in the film era. Modern digital cameras can adjust their sensitivity to light in real time, allowing photographers to see the results of different exposure settings immediately and make adjustments accordingly. Digital sensors are also more sensitive to the blue wavelengths that are prominent in moonlight, often producing more accurate color reproduction than film-based systems. However, digital moonlight photography has also revealed new complexities in accurately representing nocturnal illumination. Digital sensors and display devices have different characteristics than human visual perception, sometimes capturing or displaying details that aren't visible to the naked eye, or missing subtle effects that human vision can detect. Learning to process digital moonlight images to match the subjective experience of observing moonlit scenes has become a sophisticated art that combines technical knowledge with artistic sensitivity. Time-lapse photography has opened new possibilities for documenting how moonlight changes over time. By taking photographs at regular intervals throughout the night, photographers can create sequences that show how the quality and direction of moonlight shifts as the moon moves across the sky. These time-lapse sequences reveal patterns of illumination, change that would be impossible to observe in real time, showing how shadows creep across landscapes and how the color and intensity of moonlight varies with atmospheric conditions. Scientific photography of moonlight has contributed important information to research in astronomy, atmospheric science, and ecology. Standardized photographic techniques allow researchers to document and measure variations in moonlight intensity, color, and polarization under different atmospheric conditions. These measurements help scientists understand how atmospheric composition affects the transmission of moonlight and how changes in air quality might influence the biological and ecological effects of lunar illumination. Video technology has made it possible to capture the subtle movements and changes that characterize moonlit scenes, the gentle swaying of vegetation in night breezes, the movement of nocturnal animals, and the gradual changes in illumination as clouds pass across the moon. High-sensitivity video cameras can now record moonlit scenes in real time, revealing the dynamic nature of nocturnal environments that still photography cannot fully capture. Infrared photography and imaging have revealed hidden aspects of moonlit scenes that are completely invisible to normal human vision. Infrared radiation from moonlight creates patterns of heating and cooling in landscapes that show up clearly in thermal imagery, revealing how different materials absorb and emit infrared radiation under lunar illumination. These thermal patterns provide information about surface composition, vegetation health, and animal activity that adds new dimensions to our understanding of nocturnal environments. The challenges of capturing moonlight have also driven innovations in display technology and image processing software. Accurately reproducing the subtle tonal gradations and color variations of moonlit scenes requires display devices capable of showing fine distinctions between similar shades of gray and blue, software tools for adjusting the contrast, color balance, and tonal range of moonlight photographs have become increasingly sophisticated, allowing photographers to fine-tune their images to match their subjective memories of moonlit scenes. Artistic interpretation of moonlight photography has evolved to encompass both documentary and creative approaches. Some photographers strive for maximum accuracy in representing exactly what moonlit scenes look like to human vision, while others use the unique qualities of photographic processes to create interpretive images that emphasize the emotional and aesthetic impact of moonlight rather than literal accuracy. Both approaches contribute to our appreciation and understanding of lunar illumination. Whether scientific or artistic, the democratization of photography through smartphone technology has made moonlight photography accessible to millions of people who would never have attempted it with traditional cameras. while smartphone cameras still face significant limitations in low-light conditions. Computational photography techniques are rapidly improving their capability to capture moonlit scenes. Apps that combine multiple exposures, adjust for camera shake, and optimize settings for night photography are making it possible for casual photographers to document and share their experiences of moonlight in ways that were previously impossible. As we near the end of our gentle journey through the world of moonlight, let's turn our gaze toward the future and explore how our relationship with lunar illumination might evolve in the coming decades and centuries. The story of moonlight is far from over. In fact, we may be on the verge of the most exciting chapter yet. As human space exploration returns to the moon and our scientific understanding of lunar processes continues to deepen through advanced technology and direct investigation, the next decade promises to bring humans back to the lunar surface for the first time since the Apollo missions ended in 1972. NASA's Artemis program, along with lunar exploration efforts by other space agencies and private companies, will establish permanent human presence on the moon, fundamentally changing our relationship with our closest celestial neighbor. For the first time in human history, people will experience moonlight from the moon itself, standing on the lunar surface and watching Earth hang in the black sky like a blue and white marble. This new perspective will undoubtedly transform our understanding of the light exchange between Earth and Moon. Astronauts on the lunar surface will witness Earth-like sunlight reflected from our home planet that illuminates the lunar landscape much as moonlight illuminates Earth's surface. During lunar night, which lasts about 2 weeks, Earthlight will be the primary source of illumination for lunar bases and activities. Earth appears about 4 times larger in the lunar sky than the moon appears from Earth, and with its bright clouds and reflective oceans, Earth actually provides much more illumination to the moon than the moon provides to Earth. The establishment of permanent lunar bases will create new forms of artificial illumination that will be visible from Earth. Solar panels, habitat lights, and industrial facilities on the moon may eventually be bright enough to observe from Earth with telescopes, adding human-made light sources to the natural lunar illumination we've known throughout history. These lights will serve as beacons of human expansion into space, visible reminders of our species' growing presence beyond Earth. Advanced lunar research facilities will provide unprecedented opportunities to study the processes that create moonlight. Instruments placed directly on the lunar surface will measure exactly how different materials reflect sunlight, how the lunar surface changes over time due to space weathering, and how variations in solar output affect the brightness and spectrum of reflected moonlight. This research will not only improve our understanding of lunar science, but will also contribute to studies of other airless bodies throughout the solar system. Future lunar exploration may also reveal resources that could be used to modify the moon's reflective properties. If substantial deposits of water, ice, or other materials are discovered in lunar polar regions, their extraction and processing could create new types of surface features that reflect sunlight differently than the ancient rocks and soil that currently dominate the lunar landscape. Large-scale mining or construction activities might create temporary changes in local surface reflectivity, subtly altering the pattern of moonlight visible from Earth. The potential for lunar industrial development raises fascinating questions about how human activities might change the character of moonlight over time. Solar panel arrays, mirror systems for concentrating sunlight, and other technological installations could create new patterns of reflection and shadow on the lunar surface. While these changes would likely be too small to detect with the naked eye from Earth. They could be visible through telescopes and might represent humanity's first deliberate modification of a celestial body's appearance. Climate change on Earth is already beginning to affect how we observe and experience moonlight. Increasing atmospheric pollution and changing weather patterns influence how moonlight is transmitted through Earth's atmosphere, potentially altering its color, brightness, and clarity. Rising sea levels and changing precipitation patterns will modify the reflective properties of Earth's surface, which in turn affects how much Earthlight illuminates the lunar surface during its nighttime. Periods. Light pollution continues to spread as urban areas expand around the world, making natural moonlight less visible to growing numbers of people. However, this trend has also sparked increasing interest in dark sky preservation and astronomical tourism. Future conservation efforts may establish larger protected areas where natural lighting conditions are maintained, allowing future generations to experience moonlight as humans have throughout most of our history. Advances in artificial lighting technology may also help reduce light pollution while maintaining the benefits of nighttime illumination for human activities. LED lighting systems that can be programmed to minimize interference with astronomical observation are becoming more common, and future smart lighting networks might automatically adjust their output based on lunar phase, weather conditions, and local needs. This could allow urban areas to maintain necessary artificial lighting while preserving some ability to observe natural moonlight. Scientific understanding of moonlight's effects on Earth's ecosystems will likely expand significantly as researchers develop better tools for studying nocturnal environments. Advanced remote sensing systems, automated wildlife monitoring equipment, and long-term ecological studies will reveal new details about how lunar cycles influence plant and animal behavior. This knowledge may inform conservation strategies and help us better understand the complex relationships between celestial cycles and terrestrial life. The growing field of astrobiology, the study of life in the universe, is beginning to consider how different types of illumination might affect the evolution of life on other worlds. Understanding how moonlight influences life on Earth provides important clues about how reflected starlight or other forms of secondary illumination might create habitable conditions on planets and moons throughout the cosmos. Future discoveries of life on other worlds may reveal that the gentle, reflected illumination we call moonlight represents a common and important factor in the development of complex ecosystems. Advances in virtual and augmented reality technology may eventually allow people to experience moonlight in entirely new ways. Virtual reality systems could simulate the experience of observing moonlight from different locations in the solar system, showing how Earth's moon would appear from Mars, Jupiter, or other worlds. Augmented reality could overlay historical information about lunar phases, astronomical data, or cultural interpretations onto real-time views of the moon, enriching people's direct experience of lunar observation. Educational applications of moonlight study will likely become more sophisticated as digital tools make it easier to track, predict, and understand lunar phenomena. Students around the world may participate in coordinated observations of moonlight intensity, color, and effects, contributing to citizen science projects that gather data about lunar visibility under different atmospheric conditions. These educational initiatives could help maintain human connection to natural astronomical phenomena, even as urbanization continues to reduce direct exposure to dark skies. Future space missions beyond the Earth-Moon system will carry our understanding of reflected sunlight to other worlds. Missions to asteroids, other planets, moons, and eventually other star systems will encounter new forms of reflected illumination that will expand our definition of moonlight to include any secondary illumination created by sunlight or starlight bouncing off airless surfaces. The moons of Jupiter and Saturn already provide examples of complex lighting environments where multiple sources of reflected light create intricate patterns of illumination and shadow. As human civilization potentially expands to other worlds, settlers on Mars, the asteroids, or moons of the outer planets will experience their own versions of moonlight. Reflected sunlight from local moons, creating gentle nighttime illumination for human activities. These new forms of moonlight will undoubtedly inspire new forms of art, literature, and cultural expression, just as Earth's moonlight has throughout human history. The fundamental human fascination with moonlight shows no signs of diminishing as we advance into an increasingly technological future. If anything, the contrast between artificial environments and natural phenomena may make moonlight even more precious and meaningful to future generations. The gentle, reliable illumination that has guided human activities and inspired human creativity for thousands of years will likely continue to serve these roles, regardless of how dramatically our technological capabilities expand. As our gentle exploration of moonlight draws toward its close, we find ourselves enriched by the remarkable journey we've taken together through time, space, and human experience. From the violent cosmic collision that created our moon billions of years ago to the cutting-edge research that continues to reveal new secrets about lunar illumination, we've discovered that the simple act of moonlight reaching Earth represents one of the most complex and beautiful phenomena in our solar system. The story we've shared reveals moonlight to be far more than just reflected sunlight. It's a bridge between Earth and cosmos, a timekeeper that has regulated life for millions of years, a muse that has inspired countless works of art and literature, and a gentle presence that continues to offer comfort and wonder to anyone who takes a moment to step outside and look up at the night sky. Every beam of moonlight carries within it the history of our solar system, the physics of electromagnetic radiation, the chemistry of lunar rocks, and the biology of countless organisms that have evolved to dance to lunar rhythms. We've learned that the moon's formation through catastrophic collision created not just our satellite, but the very conditions that allow complex life to flourish on Earth. The gravitational stability that the moon provides, the tidal forces that may have helped life transition from sea to land, and the regular cycles of illumination that have guided evolution for eons all stem from that ancient cosmic accident that gave us our lunar companion. In a very real sense, every moonbeam represents a gift from the violent birth of the solar system, transformed into gentle beauty through billions of years of orbital evolution. The phases of the moon, which create the ever-changing patterns of moonlight intensity we observe throughout each month, remind us that we live in a dynamic, interconnected system where the movements of celestial bodies create predictable rhythms that extend from the largest ecological patterns down to the molecular processes within living cells. The same gravitational forces that create tides in our oceans also help stabilize Earth's rotation and climate, making our planet a haven for the diversity of life that depends, directly or indirectly, on the cycles of lunar illumination. Through our exploration of how different creatures respond to moonlight, we've discovered that humans are part of a vast community of life that has learned to use lunar cycles for navigation, reproduction, feeding, and countless other essential activities. The nocturnal world that awakens under moonlight reveals parallel ecosystems that operate according to different rules than the daylight world we know best, yet are equally complex and perfectly adapted to their particular environmental conditions. Understanding these relationships helps us appreciate our own place in the larger web of life that connects all organisms on Earth. The cultural dimensions of moonlight reveal the deep human need to find meaning and beauty in natural phenomena. Every culture that has ever existed has developed traditions, stories, and beliefs surrounding the moon and its gentle illumination. These cultural responses represent one of the most fundamental and universal aspects of human nature, our drive to connect emotionally and spiritually with the cosmos that surrounds us. The fact that moonlight continues to inspire artists, poets, and dreamers in our modern technological age demonstrates that this connection remains as powerful today as it was for our earliest ancestors. Scientific study of moonlight has revealed the remarkable precision and elegance of the physical processes that create the illumination we see, from the nuclear fusion reactions in the sun's core that create the original light, through the complex interactions with lunar surface materials that modify and redirect that light, to the atmospheric processes on Earth that filter and focus it before it reaches our eyes. Every step in moonlight's journey demonstrates the beautiful complexity of natural systems. Understanding these processes doesn't diminish the wonder of moonlight. If anything, it enhances our appreciation by revealing the intricate choreography of physical laws that make such beauty possible. The subtle influences of moonlight on human biology and behavior remind us that we remain connected to natural rhythms, despite our increasingly artificial environments. While we may no longer depend on moonlight for practical illumination, our bodies and minds still respond to the ancient cycles that governed human life for thousands of years. Recognizing these connections can help us make choices about lighting, sleep, and outdoor activities that support our health and well-being. By honoring our evolutionary heritage, the artistic and photographic documentation of moonlight represents humanity's ongoing effort to capture and preserve experiences of natural beauty. Each successful moonlight photograph or painting represents a victory over the technical challenges of representing subtle illumination. But more importantly, these images serve as bridges that allow people to share their experiences of moonlit wonder with others. In an age when many people have limited access to dark skies and natural moonlight, these artistic interpretations become even more valuable as ways of maintaining cultural connection to lunar beauty. Looking toward the future, we can anticipate that human relationship with moonlight will continue to evolve as we expand our presence in space and deepen our scientific understanding of lunar processes. The establishment of permanent human settlements on the moon will create entirely new perspectives on the light exchange between Earth and its satellite, while advanced research techniques will reveal ever more intricate details about how moonlight is created and transmitted. These developments will undoubtedly generate new forms of artistic expression and cultural meaning around lunar illumination. Yet regardless of how our technology advances or how our scientific knowledge expands, the fundamental experience of standing under moonlight and feeling connected to something larger than ourselves will likely remain unchanged. The sense of peace, wonder, and perspective that comes from contemplating the gentle light of the moon speaks to something deep in human nature that transcends technological progress. This timeless quality of moonlight ensures that it will continue to serve as a source of comfort, inspiration, and beauty for future generations. The conservation of dark skies and natural lighting conditions represents one of the most important environmental challenges of our time. Not because light pollution threatens our survival, but because it threatens our connection to the cosmos that has nurtured human imagination and spiritual development throughout our history. Preserving access to natural moonlight for future generations requires conscious effort and planning, but the rewards continued access to the beauty, wonder, and biological benefits of natural illumination cycles justify these efforts. As we conclude our exploration, we can reflect on how moonlight serves as a perfect metaphor for the kinds of natural phenomena that make life on Earth so remarkable. It's simultaneously simple and complex, familiar and mysterious, practical and beautiful. It connects us to the largest scales of cosmic evolution while influencing the most intimate aspects of our daily experience. It demonstrates how the universe creates beauty through the operation of physical laws, and how human consciousness can recognize and appreciate that beauty in ways that seem to transcend purely biological needs. The next time you find yourself outdoors on a clear night when the moon is visible, take a moment to remember the incredible journey that moonlight has taken to reach you. Consider the ancient collision that created the moon, the nuclear processes in the sun that generated the original light, the complex chemistry of lunar rocks that reflects and modifies that light, and the sophisticated biology of your own eyes and brain that allows you to perceive and appreciate the beauty of what you see. In that moment of awareness, you become part of the continuing story of moonlight, a conscious participant in the cosmic dance that connects all things across time and space. Moonlight reminds us that we live in a universe where beauty emerges naturally from the interactions of matter and energy across vast scales of time and space. It teaches us that wonder and scientific understanding can coexist and enhance each other, rather than competing for our attention. Most importantly, it demonstrates that some of the most profound and meaningful experiences available to human consciousness require nothing more than the willingness to step outside, look up, and pay attention to the gentle gifts that the cosmos offers us every clear night. In closing, let us carry forward the sense of wonder and connection that moonlight inspires, using it to motivate continued exploration, continued learning, and continued appreciation for the remarkable world we inhabit. The story of moonlight is ultimately the story of our place in the cosmos, beings capable of understanding and appreciating the beauty that emerges from the fundamental processes that govern reality itself. In recognizing and celebrating this capacity, we honor both the cosmos that created us and the consciousness that allows us to experience its wonders. Thank you for staying with me through this peaceful journey into the story of moonlight. Reflections in darkness. I hope that our time together has enriched your appreciation for the gentle illumination that graces our nights and deepened your sense of connection to the cosmic processes that make such beauty possible. May you find continued wonder in the simple act of moonlight reaching Earth, and may that wonder inspire you to look for similar beauty and meaning in all the natural phenomena that surround us every day. Sweet dreams, and may your nights be blessed with the silver light of our faithful celestial companion.